Hey guys, so I've already degreed my cam, but what I have not done is when you degree a cam, you typically are just verifying that the valve events match your cam card, and that's important. So if you need to advance or retard the cam, but the one thing that you need to look at is not just those events, but you also need to look at a couple of other different events. One of those being at the each lift value. Now, I don't want to turn my engine over a whole bunch of times, so I'm only going to do 100, 2, 3, 4, 5, and 600 thousandths lift. And now, what we did was lobe lift before I did. So I had already shown you this. So this is my current custom one-off cam, billet solid roller cam. It's very similar to my old cam as far as duration under the curve, and we'll get more into that conversation later. But what I'm going to do tonight is I didn't video degreeing the cam on Old Red, so what I want to do this time is I'm not going to go through the entire cam degreeing up here, but what I am going to do is degree it at these lift values, and just talk about a couple things you need to do when you're degreeing cam. So the first thing is you need to use a solid lifter. Okay, so these are weight reduction style sportsman comp solid rollers. This is just an adjustable push rod, and I've got that set on a gauge here, and it's zeroed out right now. And then I've got one that's looking at the piston head. So this is going to show us when we're at top dead center, and this is going to show us how much lift we have. Now this is lobe lift, so you got to multiply that. Okay, so this is lobe lift. So it's 16 degrees at 400 thousandths of lobe lift. Well, 400 thousandths of lobe lift is 600 thousandths lift at the valve with a 1:5 ratio rocker. I need to make that very, very specific. This is a 1.5 to 1 rocker. Okay. So these valve events, so if it's a 1.6, it'll be different. So this is multiplied by 1.5 to get 100 thousandths lift. And to do this, you just get 200 thousandths lift, divide it by 1.5, and that'll give you what lift you need to test your duration at. Okay, so at 50 thousandths lift, my camshaft's 243, 257. It's on 112 degrees lobe separation angle, which is basically your two center lines divided by 2, and then how advanced it is. These are the valve events: when it opens, when it closes, yada yada. Okay, so right now I'm at top dead center on the compression stroke, and I've zeroed out my gauge here. So neither the intake or the exhaust valve are currently open because I'm on the compression stroke. So this is basically the spark plug firing, and we're gonna start going down. Now, you just need to get a piece of wire. It doesn't matter what it is. This is actually a land marker that I bolted down, and you just want to zero that out. Okay, so we're sitting at top dead center on the compression stroke. That's where I left it because that's where you want to set it up when you're getting ready to put your timing set on, or your distributor. You want to be at top dead center on the compression stroke, and then do your 1843657 on your spark plugs. So hopefully you can see pretty good right there. It looks like you can. All you need to see is this top part where my marker is. And so when you do this, I'm just going to do one on video. I'm not going to go through this entire thing, but we'll talk about a few points. So let's go ahead and come off of compression. So the spark plug is just fired. We're going down. And so you're going to start seeing the exhaust valve open. You're not going to see it because right now my push rod is only on the intake valve. So we're just going to keep going. All right. So we're coming back up to top dead center. And soon our intake valve is going to open and our exhaust valve is going to close. So we've already seen it happen. So let's go back. If you look here, let's go back to 0. Okay. And let's just get that perfectly zeroed out now. There we go. All right. So as soon as I start moving, let's go, go, go. All right, right there. Okay. So the lobe starts to move. Now this is what's called seat timing. It's something I didn't measure before because normally it doesn't matter a whole lot because you don't really have anything industry-wide to compare it to. Most will do 6,000 after. All right, so right there. So right now you can see that I'm 61 thousandths. Okay. I'm sorry. 66 degrees before top dead center. Okay. 66 degrees before top dead center. Now, this is when this is called seat timing. So if I were to go through the whole sweep until the intake valve closes, that's seat to seat timing. It does have relevance, okay? But right now, all I'm going to measure is the 100 thousandths of lift. And I'll show you why. So right now, the piston, and you can see the piston is still coming up, right? So we're still on the exhaust stroke. Intake valve is cracking open. All right. So now, if you notice, let me go back here. All right, that's at 0, right? So look, if we keep looking, look. So that's just over 50 thousandths. Here, let's bump it back. All right, so that's essentially 50 thousandths of lift right there. Okay. So what I want you to see here, and I've talked about this in other videos and people don't seem to believe me. So 50 thousandths lift. Guess what? We're still not at top dead center. Okay. So let's keep going. All right. So now we're coming up on top dead center. We're coming up on top dead center and whoop, just passed it. All right, so now we're perfectly at top dead center. Okay, now there's a little bit of dwell here. So it's not like we're at top dead center, but there's going to be a little bit of dwell there. So if you're looking at the cam, we're at what, 70.5 thousandths, basically 71 thousandths of lift. So if you look here, 100 thousandths lift starts at 60 or 67 thousandths of an inch. So our 100 thousandths of an inch at 100 thousandths at the valve. So basically right now when this piston's at top dead center, our valve is open just over 100 thousandths of an inch. And we're still at top dead center. The piston has not started going down the bore yet. And so here in a second, you're going to see why when I flow test cylinder heads, I really only start flowing them at 200 thousandths lift when I want to know where my RPM band really kind of starts. Because right now, we're the exhaust valve's still open. You can't see it, but the exhaust valve's still open. Exhaust valve, if you look, intake open, exhaust close after top dead center. Mine closes 13.5 degrees after top dead center. So not until we get over here. So exhaust valve's still not even closed yet. So we're not even filling the cylinder really. I mean, we are at high RPM. You've got scavenging and an inertial filling. But anyway, so now when we get, one of the numbers that we need to know is what 75 degrees after top dead center. We want to know what that is. So right now I'm not even doing duration. I just want to know how much lift at the valve do I have when I'm at 75 degrees after top dead center, because I can tell you 75 degrees after top dead center, that's when, I don't even know if you can see me over here. Hey, 75 degrees after top dead center is when you really start to pull a lot on the port, the intake port. That's when you really start to get the ball rolling on filling the cylinder. So that's really when the air starts to want to move, and I mean move really good. So let's go to 75 degrees after top dead center. All right. So here we go, here we go, here we go. And that's 75 degrees. Now, if you missed it, all right, make sure this is what you're watching, because that shows you how many thousandths of inch lift. Okay. So right here, the reason why I went back is I want to show you again, but I also want to make sure that was zeroed out. So I bumped it a second ago. So right here, all right, we're going to go 100 thousandths, 200 thousandths, 300 thousandths, and so right now, 75 degrees after top dead center, we're at 373. 373 thousandths of an inch. Now that's lobe lift, right? That's when you really start to just pull on the port. In my experience, 75 degrees after top dead center is where it's money. So you want, and now this is how I choose camshafts. You want the most duration, the place where your camshaft spends the most time and has its best flow characteristics as far as velocity, average velocity, all the things, all the stars align when you're at that lift. 75 degrees after top dead center. Okay, so my camshaft, 373 thousandths after top dead center. That's basically, I would have to do the math, and my calculator's upstairs, so I'm going to pause the video and just do the math real quick. And never mind, I'm not going to pause the video. Just give me a second. I'll be right back. Let me grab my calculator. All right, sorry about that. All right, so 373 thousandths, and we're going to multiply that by 1.5. So 560 thousandths lift. Okay. So 560 thousandths lift. And what you guys will notice, and I don't even know if I have this wrote down on this paper or not. Let's see here. So if y'all look, so at 560 thousandths of lift, this thing's at 75 degrees after top dead center. Where is my peak flow? 550 thousandths lift. When we designed this camshaft, I tried to get it around 550 to 560 thousandths lift, but that was going off of my cylinder head flow before I did any of the changes with this intake manifold, because honestly I thought this intake manifold was going to flow a little better and not have to work so hard. But if you look over here, it's even more apparent. 550 thousandths lift, that's 300 CFM on the outside runner. So this is number 5 and number 7. We've already looked at this on another video. But at 75 degrees after top dead center, I'm picking up the most flow. I'm at the part of the flow curve where it wants to be the most. Okay? So that's deliberate, y'all. That's why this cam was designed the way it was. And that's why you need to make sure when you're doing this, let me write this down, 560 thousandths lift. I never confirmed that whenever I did this degree the first time, because I was really just trying to make sure the lobes were good, because I knew it'd be a while before I had time to do this. But anyway, so that's where I'm at, 75 degrees. And then the other lift value you kind of want to know is when the intake valve closes. How far after bottom dead center, okay, does the intake valve close? How many degrees after bottom dead center? Okay, so, and this is where you kind of get to the end of the seat timing, but this is very relevant. How far up the bore is the piston? Okay, so let's just keep going. All right, that's the top of the lobe, and we're on our way back down. So we're coming down, and intake valve closes right there. Make sure it's completely done moving, and then we'll back up until we see it move again. Guys, you gotta do this real slow. The bigger your degree wheel, the more accurate this is. All right, it just started moving. So, where are we? Okay. You see these numbers? There's 2 numbers here. Okay. So that's what this says. The large are used for checking the center line. The small used for checking valve timing. Okay. So look at the small numbers. Okay. So we are 100. See this. See how we started down here at 180. This is bottom dead center here. 180. It's bottom dead center. So this is how many degrees after bottom dead center. Okay. So it looks to me like we are, and let me get your camera right centered on there. So that, look, what is that? 84? Oh, not 84, I'm sorry, 104? 104 degrees. 104 degrees after bottom dead center. So 104 degrees after bottom dead center is intake valve close. Intake valve close. I'm writing that down, but this is important because if you look at where the piston is, okay, how far down the bore it is, this is when the intake valve starts to close. So you still have quite a bit of quench there. This is a 348 thousandths stroke. So let me grab my thing here. So looking here, look at that. Just over an inch. Just over an inch before top dead center on how much stroke there is left before the intake valve actually closes. That's what's called inertial filling. So that's what you're after, is inertial filling. It's super important to get that right. So we'll get into that later. My phone battery is going to die, so I just kind of want to get this video done. So the first thing we're going to do is we're going to back up. Back up, back up, back up, back up. Back up. Alright. Make sure we're completely... And it moved a little bit because I was kind of being a little aggressive on moving it back. Normally I don't go that fast. Alright. So the first thing we're going to do is we're going to go 67 thousandths of an inch. So that's 67 thousandths of an inch is right there. Okay, so if you look at that, focus, 67 thousandths of an inch, okay, of valve lift. Where does that put us? Okay, let me put your camera here centered. Looks like we are 11 degrees before top dead center, okay? So 11 degrees before top dead center. So I'm going to write that down. 11 degrees. All right. So now I'm going to turn it until we get to 67 thousandths of a lobe lift again. Okay. All right. Here we go. So you write that down. Now you're going to cross over. Okay. You're going to cross over top dead center, and the numbers are going to start counting back up. So that's 100, 200, 300, 400. Alright. 400. It's best to just go all the way until it closes to make sure, and then work it back to we're at 67 thousandths, because it's just easier to control going this way and you get any slop out of it. 60. See? Right there. Alright. So, where are we at? We're at 140 degrees. Okay? Now, if you look, we were going around here, right? So, you got to keep in mind, we went from top dead center. You got to use these little numbers here, because you can use the big numbers until you get to 180 degrees. Sorry. Okay, we were at 0 degrees. Okay, you're going around. You see how we got to 180 here, and then it starts coming back down. So what does that show us? That's 40. See the little number there? That's 40 degrees. Okay. 0. All right. Then you come down here. That's 10. And they count. So basically all you're doing is you're adding these up. Okay. So we're 11 degrees before top dead center. Okay. And then you got to add 180. Okay. Because we traveled 180 degrees. Okay, half a circle. So plus 180. Plus, how many degrees past 180? Okay, 40. See the small one? That's your seat timing. Or not seat timing, but that's your valve event timing. So 40 degrees. All right, so these numbers added together is your total duration. Okay, does that make sense? So let's see, 180, 90, 100, 210, 220, 230, 1 degrees. Okay, so 231 degrees of duration at 100 thousandths lift. Now, if y'all noticed, the piston at 100 thousandths lift, see, now we're almost down there. We're not far from all the way down the bore there. That's basically all you do. I mean, it's super simple. People make this out to be a hard thing. So then you would just go back up to 133 and you can go backwards. So we can back this up. Okay. So we're at 67. I'm going to set the camera down now so I control this engine. So back this up. So that's 100, 10, 20, 130. What did I say? 133. Sometimes it's really hard to move this thing just that little bit. Okay, so that's 133 thousandths of lift. What are we at? We're at, look at 161, which is 20 degrees after 180, right? So what we're going to do is we're going to write down 20. Not just to make that page look clean, I'm just doing it on another page. So 20 plus, okay, so that's 20 degrees before our 180. Okay, sit you back down. And we're going to go all the way through. All right, so if you noticed, we went through 180 over here, right? We were 20 degrees before, okay? And we're coming back. So now, see how it's 0, 10, 20, 30, 40, 50. So right now we're 80 degrees. Okay, we're gonna keep going. Whoops, keep going. And so we're going to go all the way to before top dead center. Verify that we're on 0 degrees. We were. Not 0 degrees, but 0 lift. And we'll come back up to 133 thousandths. And we'll just pass it a little bit so that the degree wheel's going in the same direction it was. And I have better control. There. Now, back at 133 thousandths lift. And where we end up. So, we ended up at, if you look here, so we're, what's that, 5, 6, 7. So we're 7 degrees after top dead center. Okay. So you basically just take 180, 180, sorry, I'm doing this through the camera, 180, and you're going to subtract what's left right here, okay? So you're just going to take 7 away, minus 7 degrees, so 173. Okay, that's all you do. And then you're just adding 20 to that. So, if you want to do that, it's simple. Okay, so 193 degrees. Okay, that's all you do. So 230 degrees at 100 thousandths lift at the valve, 193 degrees of duration at 200 thousandths lift at the valve. This is 200 thousandths of lobe lift, which is in a completely different part of the curve than this. Because this is 100 thousandths of lobe lift, this is 133 thousandths at the valve. Okay, this is 133 thousandths of lobe lift to get 200 thousandths of lift at the valve. Okay, so these numbers are not the same thing. This is times my 1.5 ratio rocker to give me what the duration is at that lift. So I'm going to finish these other ones, and then I'll come back on here with the total sweep and show you the comparison there. I'll be back. Alright guys, so I finished those out, and so here's what I really wanted to get to. This is the punchline of this whole video. So I told you at 75 degrees after top dead center, okay, you're just over an inch down the bore, about 1.25 inches down the bore, and that's when you really start. The exhaust valve is completely closed, and you are going down the bore, and you are officially putting a huge draw on the intake port. So this is where you want peak flow, and this is where you want the lobe to spend the most amount of time. So this is how you choose a camshaft and how you pick when you want the best part of your port to flow. And so what you normally do is you develop the cylinder head, and then once the cylinder head's developed, then you choose a camshaft that supports the peak flow of that cylinder head. This is why you don't choose a camshaft and then build a cylinder head around a camshaft. You do the cylinder head and flow it with the intake and this throttle body like I've been doing. And once you get those numbers, then you go, okay, what cam timing do I need? When do I need to open the intake valve? When do I need to close the exhaust valve? All the things. It's all about choosing these 4 points. This is all you choose, okay? I wanted my intake to open 12.5 degrees before, 13.5 degrees after. Why? Because I wanted this much overlap, okay? I wanted overlap. So this is 23, 24, 25, 26 degrees of overlap, okay? 26 degrees of overlap, and it's pretty square. It's pretty balanced on both sides. 26 degrees overlap. Why did I want that much overlap? Because I needed that much overlap to help spool the turbo on the turbine size that I chose. And we may do a video on turbocharger selection, but I wanted that much overlap because of the size of the turbine that I'm trying to spin. I'm using twin turbos, and they're going to have a 66 millimeter turbine. And in order to, I don't have 356 cubic inches trying to spin a 66 millimeter turbine. I have half of that. I have half of the cylinders are driving one turbine. The other half are driving the other turbine. So I needed 26 degrees overlap. I was actually shooting for 25 degrees overlap, but 26 degrees overlap will help spool the turbine without causing too much reversion. And you do that with cam timing. So you choose these 4 points, and I did a video on what these 4 points. These 4 points are the derivative. These are the points you choose, and then the derivative is the duration, the intake center line, the exhaust center line, which equal your LSA, and then how much advance you need to make the camshaft. Okay, so 109 degree, 115 degree center line, these are just a derivative of choosing these 4 points. And then this is just a calculation of these added together divided by 2, and then this will come in as far as the advance on how advanced the camshaft is, and that's all based on these 4 points. So I needed that much overlap because I wanted to help spool those turbines without causing too much. So I don't want too much overlap because I need vacuum. So I wanted around 10 inches of vacuum at idle. So I sized the turbine to get 10 inches of vacuum at idle so that I could use my vacuum reservoir to power brakes. But I thought I can get away with this much overlap and get 10 inches of vacuum, and then have enough in the vacuum cylinder to still use my brake booster. And as far as intake valve close, I wanted the intake valve to close around 100 degrees after bottom dead center for seat timing. And this number ended up being, this is at 50 thousandths of lift timing. So 50 degrees intake valve close, and that's 104 degrees after bottom dead center for actual seat timing, not at 50 thousandths. So, or 50 thousandths before, Anyway, so this is a good number, and if you want to know what that looks like over here, so I just got done doing this, so let's go the other way. So we're opening. All right, now we're closing, so it's 3, 2. All right, so that's about 100. Let's go till we get in. Oop. Sorry. Let's get the valve closed. All right, valve's closed. All right, so let's go back up let's go back down until the valve is just starting to move. Gotta go slow. All right, you see it? It just touched. It just started moving. So just as a visual representation, this is my engineering. See how before at 75 degrees after top dead center is when I said at 75 degrees is when you get the biggest pull, and we were at just about an inch down the bore. Well, we're about 1.25 inches from the top of the bore, just under 1.25 inches. Just under 1.25 inches. Not even actually, So, sorry, more like 1/8, 1 inch and 1/8, right? So we're essentially the same, and that's on purpose. So this is when you get the biggest draw on the port, and the port starts going stagnant around 75 degrees before top dead center, which is, if you look, this is top dead center. We're at 77 degrees before top dead center. Okay, 77 degrees before top dead center. So this was on purpose. I wanted the intake valve to close around the same point as 75 degrees after top dead center. So 75 degrees before top dead center on the intake valve close, 75 degrees after top dead center is where you want your peak flow to be. So all this to say right here, what this is this is how much duration is spent at each 100 thousandths of lift. So for the valve, once it reaches 100 thousandths till it reaches 200 thousandths lift, it spends 38 degrees at that lift value. Between 2 and 300 thousandths, it spends 30.5 degrees of duration. Between 3 and 4, as you can see, this is becoming very linear. Okay, between 3 and 4, 32.5. My phone's about to die, so if I lose you, I'm sorry. At between 400 and 500 thousandths, 37 degrees. As you can see, it's starting to go up now. And look at that, guys, 77 degrees of duration. Now, With my 16 thousandths of lash, it's just under 600. So this 16 thousandths up here, or 16 degrees up here above 6 doesn't even matter because of lash. That takes up some of it. But 77 degrees is how long my camshaft spins above 500 thousandths of lift, which is where all the meat of my flow is. And if you did 550 thousandths lift, it's pretty much just under, it's actually just over half of that, in fact. So 77 degrees above 500 thousandths lift. So as you can see, it's accelerating through these bottom mid-lift flows, and then at peak lift flow, it actually spends more time. So if you double mid-lift, that's 64 degrees that it would spend between 2 and 3, so that's still significant. But again, 77 degrees is still more. So now if you double 400 thousandths lift, it's still more than this. So this is the meat. It's going to spend 77 degrees above 500, but it's also going to spend 80 something above, 70 something again, right? Above 400 thousandths lift, because it's going to be there twice. And then again, it's going to go down here. So this is why you design a cam a certain way to peak the performance of your cylinder heads. I hope that makes sense. I went a little bit more in depth than like a normal basic. Everybody has videos out there on how you do this, but I really wanted to get into why degreeing your cam. You can see why I designed the cam the way I designed it, and why I designed my cylinder heads to flow what I did, and why I worked so hard on that number 5 cylinder to get it to flow really, really good. If I lose you, it's because my phone died, and I'll just end the video there because I'm done. But right here, boop. So I tried really hard to get above 500 thousandths lift, good CFM that was not turbulent. So before, when I first did the manifold, at 500 thousandths lift, it went freaking turbulent. And I was like, well, this is unsat. This is not going to work because the cam that I designed is not going to work here. So I designed the cam based on my flow characteristics of the cylinder head. This is not going to work. This is unsat. So I had to work on that manifold until I got this completely happy and stable. Not only did I get it stable, I picked up some flow. And over here, it just, man, it loved it. It was good up until 600, which means nothing to me, essentially, because it was 300 CFM till pretty close to 600. And I'm lifting my intake valve to 600 and, 593 thousandths lift with my lash in there. So anyway, that lash will also impact these numbers because you're arriving at this lift value a little bit later. So you don't have quite as much duration at that lift value, if that makes sense. But I'm not getting that in depth with this video. Just know that when you add lash, 100 thousandths, a lift is not 100 thousandths lift at the valve because you got to take away the lift that's removed because of the mechanical lash. So I'm running 16 thousandths of lash. So this is kind of roughly what my net lift. So 590 thousandths lift anyway. So that's it. That's all I got. That's how you degree a cam. You do the same functions I was just doing to do all this other stuff. And these are literally just the values you get here. So as soon as you see the valve at 50 thousandths a lift, what am I? Before top dead center, after bottom dead center, all the things. So anyway, hey guys. So my phone died, so I wasn't able to finish the video, but we'll call this part 2, and I'll just post it after the other one. So what I want to finish off with, cost, okay, and then some total durations. So I started to talk about this at the end of the last video. but I had not done the exhaust side yet. And so let me finish my conversation on the intake side, and then we'll come over to the exhaust. So pretty much everyone in the world and the internet, it seems like, has passed around that mid-lift flow is the most important. Well, yes, in some instances, your camshaft will kind of decide where the best flow is. So we already talked about until 200 thousandths down the lift, we're really not pulling a lot of flow, right? So, or we're not really starting to pull flow, right? So that's why we do these lift values. And I talked about 77 degrees of duration above 500 thousandths. What I didn't do is talk about the full sweep. So this was the first sweep coming up. So 38, 30, 32, 37, 77 degrees. Okay. Now that 77 degrees was from 5 to 6. Now you got to go back, because I'm at 590. We'll just call it 6 for now, because it is over 600 before lash, and I can tighten my lash up if I want. So let's just say, or put a 1/6 rocker on it. Anyway, I'm still thinking about that. So you are on your way back down. So it really starts to show, 154 degrees of duration of the camshaft is above 500 thousandths lift. That is the way my camshaft is designed. Way more important than mid-lift of 65 degrees. So you basically just double these durations, right? So you can kind of figure 74, 65, 61, 76. So 154 degrees of my camshaft duration is above 500 thousandths lift. So yes, while mid-lift flow here in the 2, 3, 4 thousandths area matters a lot, because if you add all three of those numbers up, it is more duration than this. But if you look at it, it's really not that much, right? So this is really where I was trying to get this port happy above 500 thousandths, because when I first put that Super Victor 2 manifold on there, it was turbulent above 500, and I said, that's not going to work with the way my camshaft is designed. So this is just confirming that my camshaft design is what I want it to be, and it is. So a lot of duration on the intake side. So we talked about this 75 degrees after top dead center. That's 560 thousandths lift, which is right in the middle of this band where it spends the most amount of time for a given lift value. We'll put it in that respect. And what I talked about was why this is where it starts to really draw on the port. So you kind of have to talk about the exhaust side, but let's just go to seat timing, okay? I didn't do the intake valve open seat timing because I really don't care. But these two seat timings do matter. Exhaust valve close. So that's where I'm at right now. This is where the exhaust valve is. Intake valve close, okay? So when the intake valve closes, right, you're 104 degrees after bottom dead center, okay? Now your exhaust valve opens before bottom dead center, so you have ignition and it starts to come down, right? And then it starts to come back up, and then your exhaust valve closes 62 degrees after top dead center. Well, our intake valve is already open. So this is at 12 degrees. I think it was 60 something degrees that it actually opened. But that's this right here that matters the most. Exhaust valve close. Okay. So exhaust valve close. This is where we're at right now. So exhaust valve close after top dead center. 62 degrees. I just barely bumped this thing, but right now it shows 61, but it's 62 degrees, right? And if you remember the last video we talked about, we at 75 degrees, we were at an inch in the bore. So if you look at this, you're about 3/4 of an inch down the bore when the exhaust valve finally completely closes. Okay? When the exhaust valve finally completely closes is when you really start to draw in. So you have about 1/4 of an inch down the bore, which is about 10 degrees here. Once the exhaust valve finally completely closes, about 1/4 inch of a draw is when you really start to accelerate the air inside the intake port and put the strongest pull on it. And so it takes about 1/4 of an inch of the cylinder to do that, because 1/4 of an inch, if you look at the circumference here, that curtain area, not just the curtain area, but that whole volume flow there, how much volume that is, equals about the port volume. So in my respect, about 205 cc's. So it all matters, guys. You have got to size your intake runner for that acceleration of the air, and then you've got to choose your camshaft. It's all matters. The combination matters. You don't get a lot of talk about this, and I just kind of wanted to reiterate it because I just don't hear it ever talked about in any of these how you degree a camshaft. Because degreeing a camshaft is simple. That's just basically making sure the valve timing events match your cam card. Make sure you didn't get somebody else's cam. But then you got to really get into it. All right, you got to really get in there and start making sure that you chose the right stuff. And if you didn't, get a different cam. All right, so anyway, so exhaust valve closes about 1/4 of an inch down the bore. We've really accelerated the air, and our intake valve is really starting to pull right where it spends the most amount of time. So that matters a lot, guys. And then when your intake valve starts to close, again, you've got about a very similar amount of duration all the way down the sweep at each one of those lift values. So yes, mid-lift flow matters a ton. You gotta have good flow here because it still spends a shit ton of time. A lot of time in that area. But up here, guys, this peak lift flow, in my respects, matters a lot. Now, if you have a camshaft that's not as aggressive as mine, and you have a lot more tame camshaft, then it will not spend as much duration up here as it will in the mid-lift. So keep that in mind. This is completely camshaft dependent, and everything will matter. So going to the exhaust side, you can see it's a little bit of a difference at the very low lift of the exhaust valve. So when the exhaust valve starts to open, it spends a lot of time in that area. 144 degrees between 100 and 200 thousandths lift. So my exhaust valve doesn't flow a lot in that area. And that's kind of for a good reason. You don't want it to flow too much, because if it has really good low lift flow, when you're at this part right here and the exhaust valve finally closes, if it has really good low lift exhaust flow, then you're basically just taking intake flow and air and fuel and just shooting it through the exhaust on overlap. So you kind of want to have low exhaust flow right in here. And then, you really want it to flow really, really, really good at the high lift, because at low lift, when the exhaust valve first starts to open, so at the first half of this, so not the 74 degrees, but your first 37, 35, 29 degrees, these 37, 58, when you first open your exhaust valve, you're like 1.5 inches down on the power stroke. So you don't need to have really good exhaust flow here, because you have so much cylinder pressure still available. You want to open it early enough to help spool the turbos with some of that drive pressure from losing some of the compression that's doing work on the piston. You want to lose some of that to help spool the turbos so that you have really good transient response on the turbos. And lag and transient response are two different things. They're not the same. And I'm not going to get into turbo stuff right now, but that's why you don't want a ton of good flow here in the low lift, because you already have a ton of cylinder pressure that's going to help with flow. It's going to help with flow here. So on the flow bench, you actually don't want it to flow really good in here, and mine does not for a reason. But then it starts to pick up flow a lot, 3, 4, and 5. And 600 thousandths lift all the way to 650. It just keeps flowing more. That's why I lift the exhaust. In fact, I'll probably put a 1.6 rocker on the exhaust side for sure, to help with the exhaust. But anyway, that's neither here nor there. That's just tuning on my side to help tune the turbo response, transient response. And the AR size on the turbine housing, I can actually influence that slightly with a rocker ratio. Anyway, so then on the way back down, again, as the exhaust valve closes after top dead center, so before bottom dead center, it opens, it goes down, and then it's pushing exhaust out, it's pushing exhaust out, pushing exhaust out, and then it comes back down after top dead center. Intake valve is already open at this point, and then it closes. Well, before the intake valve opens, you basically have almost there's not a lot of exhaust gas pressure inside the chamber anymore. You've kind of equalized on the exhaust side. And in fact, the primary tube in the exhaust is actually pulling a vacuum on the chamber to try and help evacuate it. Then you start losing that because other cylinders are firing in that same header. But there's a point where you have overlap on the other side where it doesn't have as much draw. And I talked about that in a completely different header video that I did on how to choose your headers. But all that to say, all this has to work together. When your exhaust valve is almost closed, you have basically no energy left in the exhaust side, and you've equalized between intake and exhaust. And you got to get that valve closed. So you don't want it to have really good flow here, because then you start having reversion. You actually have where the pressure buildup inside the primary tube of the exhaust is greater than the pressure inside the cylinder. And you can actually get to a point, if you have really good low lift exhaust flow, where you're just going to have reversion, because the turbine on the turbo is creating back pressure, and that back pressure on a turbo side. See, this is different in A. That's why you got to have a different cam when you're in A than turbo. And it's not about this crap with duration, stage 1, stage 2, stage 3 turbos because of bigger duration and all that. It's all about valve timing events and getting this right for the combination. So yes, a supercharger, naturally aspirated blower, and all that stuff, they all need different timing events. They do. But anyway, yeah, so what I was trying to get at here, I'm trying to remember what I was going to say, but you don't want to have really good low lift exhaust flow because of that. When the turbine, you opened it earlier to get that drive pressure, or you've seen it enough, but hey, look, I didn't turn the camera off that time. Once you start driving the turbine and you start building boost, when the exhaust valve is starting to close, you no longer need that drive pressure anymore. The intake valve is open, so all that work you did to get the turbine moving before the intake valve opens, you put that work into getting the turbine moving so that you can have that differential pressure in the intake port to the chamber. So you no longer need the aid of the exhaust scavenging, because the cylinder pressure is going to get greater. But if you have really good exhaust flow on the low lift, you actually will build too much turbine pressure. And if your wastegate's not big enough, you put back pressure, and at really high RPMs, at a lot of flow, a lot of exhaust gases, you're going to build back pressure. And if your turbine size is not right and your wastegate size is not right, that back pressure gets more than the boost pressure. And once it's greater than the boost pressure, hey, it's going to go in the path of least resistance. So flow always goes from the high to low pressure. It's all about delta P, differential pressure. And if the back pressure that the turbine is creating is greater than the boost pressure, and you have really good exhaust flow on the low lift value, it actually is just going to pump that exhaust gas right back into the chamber, and it's going to displace fresh oxygen enriched air fuel ratio or air fuel mixture coming in, and that's bad. You don't want that. You lose power, and that's where your RPM just goes, and your engine just starts dying. It happens at some point. You're going to get there. But anyway, I just wanted to finish that off. I'm going to make this a completely different video because it's a little longer than I was thinking it was going to be. But again, I just wanted to show you, I left it here. This is how far the cylinder or the piston is down the cylinder when the exhaust valve finally closes 62 degrees after top dead center. And 10 more degrees later, your intake valve is at 560 thousandths lift, and boom, it's really pulling in some flow. 154 degrees above 500 thousandths lift on this camshaft. So this ought to work really good, and should be a pretty awesome stout combination. Yep.